failure is my answer. We backed it up. I told you yesterday a very brief story. When I first introduced, they thought I didn't know anything about concrete, all these big people, and we backed it up. That is where I talked about the deformability factor, the energy issues. I don't have a slide. That paper was well received.
By adding these fibers, even glass fibers, carbon fibers, many type of fibers, we are adding to concrete and we are increasing the tensile strength. And in such cases, if we can increase the tensile property and the stiffness effect, the tension stiffening, which is better than the compression failure.
When you say you're adding, you're talking about fiber reinforced concrete. Again, I have a very good friend by name Suru Shah. He did huge amount of work in the fiber reinforced concrete. When it came to designs of the structural members, honestly, it didn't take off. If I say that to Suru Shah, he's going to shoot me, but it's not in the code, let's say it that way. I'm going to speak in terms of actual terms, okay? If it is all that good, which is good, I mean, my house floor, my driveway is a long driveway. Would you believe my student built it? Of course, he became a contractor, and not a single crack after 20 some years, Fiber concrete. So I have nothing against fiber concrete, but for whatever reason, they have not introduced and taken advantage of that as a structural material, having strengths higher or whatever, or both bending and all that. No.
Actually, it depends on which type of macro or micro. For single and these things, micro fiber will be okay, but macro.
No, maybe you should run some tests for tension failure with the fiber concrete and see how that behaves. That's what I'm saying. We don't have money. If I write a proposal, I want to do concrete research, they are not going to give me a dime. That's why we are not doing it. Most of US is not. Whereas the Canadians are doing a lot of work the Chinese are doing a lot of work in that area.
So what's the primary application in US of FRC bars?
Oh, we have a lot of applications, not one.
Most prominent.
Oh, the bridge decks is one, and concrete contact with the ground is another, and the most important one is the approach and the exit slabs at the toll booths where they have this magnetic interference problem.
Yes.
Yeah, that's a big. So a lot of the rehabs are done with FRP at these exit entrance levels of the toll booths. And now they're routinely applying FRP with the MRI locations, like the hospitals where they have.
Medical applications.
Yeah, that's the MRI. Yeah. So it is growing. We built a few structures. I showed you one or two of them, the housing area type thing. I was telling him he should aggressively get into using FRP for housing structures in India, because there is no corrosion type issue. We are not doing very much, mind you, but that's an area we should. I may be promoting that because, as I told you yesterday, we are developing a mass production factory with geopolymers. You remember I told you that factory right now, we are not going to start it till next year, mass production, but that factory is going to be right now using steel. So I'm going to ask them, they rely on me for the technical part, So I'm going to see if I can eventually switch to GFRP. I don't know that, but that's my thinking. I didn't tell them yet, but that's what I'm thinking.
In connection to the geopolymer complete with GFRP bar.
GFRP bar.
GFRP bar.
Right.
Geopolymer concrete has already one activated alkali region, so its pH value is also.
We are hoping that you will see from that my 300-page report, if you properly make a GFRP bar, it will have no effect from ASR. That is, the word is properly, a lot of code languages here, but that's where the challenge is. You see, madam?
Talking about the housing domains, are GFRP beams more sustainable in cantilever effects?
Good question. In cantilever, as you know, primary failures are intention.
Yes, sir.
So I don't know whether we want to use GFRP in a cantilever scenario where tension is a dominant failure.
Yes, sir.
So the coefficient of this GFRP, coefficient of thermal expansion is around 6 to 10.
Is what?
6 to 10 into 10 to the power of minus 6.
That is for steel. For FRP, it is between 2 to 5.
And the concrete is around 12 into 10 to the power of minus 6.
Oh, I'm sorry. You and I are talking about two different units. When I said 2 to 5, I mean with Fahrenheit. So you multiplied with 1.8 or 2. So we are talking about 4 to 9. So you got it? For Celsius, what you're talking now, I'm in line with you. So that's what it is. Now, there may be some variation there. Like I indicated to you, whatever the variation you have to, that strain in itself is not the issue. It is the strain multiplied by modulus is the issue. That's what I was showing you there. Yeah, you see, sometimes I feel I'm talking to myself. You see here? The radial direction is 25. That's the strain. I multiplied it with a 50 factor, meaning there's a temperature differential of 50. That's just a bit high, but that's okay. But my E value is very, very low. Therefore, the amount of stress induced is low. Therefore, that doesn't have a lot of effect. Sometimes, I told you, nobody asked me a question, I'm glad you didn't. I said I built a jointless bridge. You remember I said that, my McKinley wheel bridge? That's going to expand and contract, right? And that's going to crack, and it did crack, for example, due to whatever reasons. So what in US we are doing is, we let a bridge crack and then clean the crack and grout it. You see what I mean? High pressure grout, no doubt. Not the kind of housing grouts you have that peel off, no. And what did you do? You have created an excellent kind of pseudo joint.
Yes, sir.
You see? One administrator in US, he built all the buildings, but he didn't put any pavement. So everybody was worried, what's wrong with this guy? So you know what he did? He waited 2 years, see how the students are walking, what direction they're walking, and then he figured out how the grass is beaten up, and then that's where he put the pavement. Right, that's what he did. So likewise, we are finding a jointless bridge, let it crack, find exactly where it is cracking, open up that a little bit, clean it up, put a high strength grout. So the grout has a certain ductility to it, therefore it doesn't open up. somebody else has a question.
So when we feel the crack, then it will cause additional stresses. Because the bridge strength was contracted.
It would relieve the stress. Where would it crack? Where you have extra stress.
And when we feel it, then it will create additional stress.
It does not. It's going to form a hinge. Remember, partial hinge. Okay, these are all called integral abutment bridges. I didn't want to use that word. Originally, when we did the work, we used to call it jointless bridges. So anyway, the answer to your question is, you are relieving the stress partially, not fully, and then grouting it. Therefore, you are not causing any additional. Whatever the additional stress induced due to cracking is already induced. See what I mean? The extra stress. It is that's the catch. You understand?
So I was thinking that when we feel the crack, then the additional movement which might happen in the future.
It already happened. It's now acting like a hinge at that cracked zone.
But there are some movements because of temperature variation and also due to vehicular movement.
That is why we have the elastomeric based grout that would take care of the temperature movements. You see?
There is one question in online
Uh-huh.
that TG minus 30 degree Fahrenheit that you do. So asked to little explain that. Why?
Okay. They can hear, right? No problem hearing?
Yes.
Oh, okay. Okay. TG is the glass transition temperature that is about 210 degree F. The purists say that the resin, even though it is cured, is going to kind of get softened from about 100 degree F. That's what they say. But I gave you a formula, if you look at it, that the rate of strength degradation beyond 100 degrees, I gave you a formula, but that's getting too complicated from a designer point of view. Therefore, what they are saying is 210 minus 30, which is 180 degree F, up to 180, 170 degree F. We are saying that there is no reduction needed. No thermal reduction factor is needed due to higher temperatures. Now, these are not ambient temperatures, please note. These are contact temperatures of the surface. You will never reach an ambient 170 or what. That's not, even Arizona deserts don't have that. But the contact temperatures are 170, 180 very easily. So only then you have a reduction factor, and then we gave you that reduction factor. But like I said, purists always say no, from 100 degree F plus, meaning above 100 degrees, it's going to start reducing the stress. So that I leave that to you. I gave you the equation, what happens after 100 degree F in terms of the reduction. You can use that, or if you just want to follow the code, follow it as, okay, if I have exceeded T minus 30 or T minus 50, whatever that reduction factor comes out, you're going to use that.
Even the hydration of the concrete also
Creates
involves some temperature that's
right.
almost closer to that value.
That's right.
50 degrees or 60 degrees.
Correct. But the point is that is temporary.
Temporary. Yes.
Right. Whereas here, you are talking about 10 hours or 12 hours in a given day, and it's a repetitive thing. This is what we call a thermal fatigue. So you need to be careful about thermal fatigue. Any other?
I have a question about the previous slide, all the columns, scatter columns. There's a M1 and M2 moments are given. These are the abstracts and binary moments. This M1 and M2.
It depends on your design. You're talking about these, right?
No, sir, about the section.
Oh, I'm sorry. This one.
Yes.
Look, a column has 4 different phenomena. It can be a pure compression. It can be a single axle based bending coupled with compression. It could have a biaxial based bending moment plus compression. It could have all those 3 plus torsion. Right? Okay. All we are talking here, M1 and M2, is if the column has single curvature versus a column having a double curvature. That's all we are talking. So if it is a single curvature, please look, M1 over M2 is negative, the column is bent in single curvature, positive if it is a double curvature. Obviously, if it is a double curvature, you will take more load. And that is why, if you look at the equation, what is KL over R? If it is a positive value, well, let's assume for a minute M1 is equal to M2, that is 41. If on the other hand, if it is a single curvature, that's a negative value, the value is 17. That's what we are talking about. That's in one direction, we agree with you. Now when we deal with the interaction curves, we will discuss how that goes. By the way, they don't have an interaction curve of double bending, 2-axis bending. They only have, yeah.
Actually, why we have reduced the I value for this design?
Okay. Why reduction? When you have bending, it's going to crack.
Yes.
When it cracks, there are 2 kinds of crackings. Okay. Now, if I don't go to the ultimate value to failure, ultimate I said, you know, the depth of the neutral axis at ultimate, do you know? Less than 10%. That is called I cracking. But we don't go there. What do? We operate, I told you many times, perhaps slightly above initial cracking. That is called I effective. To account for I effective, for all the analysis purpose, at least the preliminary analysis purpose, they use these as a guide. Remember, all these are guides. In a concrete, in any design, I don't know how many of you are designers, but let me make a broad statement. In any design, what comes first? Do you know whether the egg came first or the chicken came first? I don't know that, but same here. Without knowing the cross-sectional size, I cannot proceed. But I don't have an analysis without a cross-sectional size. So where do I start? That is what this is. This is giving a guide.
Base.
Just a guide. That doesn't mean this is right. So we use this, then we reiterate it if need be. You understand what I'm saying?
Yes.
So for the column case, for the steel reinforced concrete columns, we don't have any reduction for the columns. But for the FRB columns, we have taken 60%. It is due to increased cracking.
Wait a minute, just a minute, wait. Read this. Stiffness for steel reinforced concrete is 0.5 Ig for beam, 1.0 Ig for column. Yeah. So we are primarily talking about this. Here, this reduction is primarily due to uncertainty associated with the FRP. Unfortunately, I'm not on that committee. I dropped out. I have other things to do. Unfortunately, nobody challenged it. I would have challenged it, you know. So, what they are saying is that at least they have granted the FRP in compression as equal to that of concrete in compression. At least that much they granted. But somebody should challenge it and say, no, it should be at least 3 times that or 4 times that, which they did not. But right now, you will see that in my future, presentations on design. They are only, I wrote that 3-4 times that FRP in compression is equal to that of concrete in compression. Even though I believe it should be much higher than that. Anything else?
Currently, we are doing the application. Simultaneously, the analysis is being done too.
And I always like to tell people, a code is a dynamic system. It is an evolving system. This is not a perfect system. We're trying to improve it based on our understanding, based on our experience, based on the failures. So as some wag said, you learn a lot more from failures than from successes, because in successes all the failures are buried in. Whereas it's a failure, you want to analyze that, and that's why the concrete guys never ever allow you with any kind of equation in a brash manner without adequate testing. Because they know you are dealing with a cracked section. You are not dealing with an uncracked section. Now, I can give you a reason, Mr. Your name is Sharma, you said? I can give you a good, I can almost come up with this number. You know that? How? A cracked section with 0.1 inch depth, and you multiply that 1/3 BD cube plus AD square, you got an answer. See how clever they are? You understand what I said? That's how they came up with. So if you understand the fundamentals, it makes it so much easier to appreciate the code. So it's amazing how much you learn while you sit around the table, people arguing back and forth with passion, Nobody is insulting anybody, remember that. But everybody has a point of view. Wonderful, but let's take a collective view and see what is the best approach. Not the ideal approach, best of what's available.
So we go to lunch. We will come back.
Analysis or design, any one of them, always have certain assumptions. And would you mind going to the one slide before? So, okay, these are the assumptions. Again, I'm coming from the US code point of view. So I need to, before I talk about these, I need to properly explain what is 0.003, what is this, especially this one, and what is this. So I'll go to, I'm coming from the US code point of view. So you have to bear with me. Okay, let me start out. You know equilibrium, right? Of forces. So if I had to learn how to draw this here, because if I am in a hurry, it's going to skip it. So Okay. Now, I'm talking about the US code. There are 3 different kinds of stress blocks that that we in the US used. This is a parabolic stress block, also known as Hogenstad's stress block. This is a trapezoidal known as Jensen's stress block. This is Whitney's approximate stress block, corresponding to that of Hogenstad's stress block. You know how we got this? That is essentially nothing but the stress-strain curve of concrete. So if you look at the stress-strain curve of concrete, that is stress versus strain. So you, on the strain axis, you flip it, that's what you're going to get. Now, that's a very difficult stress block to mathematically handle it when you are dealing with it as an equilibrium equation, right? So, of course, the resultant of it is somewhere there. That should be equal to this, right? Otherwise, it's not in equilibrium and all that good stuff. All right. And Jensen came along and it is too complicated, he did this. And then Whitney said, no, 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 it's even more complicated, and he did this, which is wonderful, easy to deal with, right? So the force from this stress block is what? The force is B times C, where B is the width. We call it A. Let's call it A. That is, if you look at the 3-dimensional view, this is the area. And you multiply that with F prime C. That will give you the compression force should be equal to AS, Fs, or F1. I'm going to leave it as Fs only because I'm going to make you understand what is a compression failure. I got some questions. I was a bit surprised. There is a misunderstanding about it. Therefore, I'm taking a little bit of time to explain it. Okay, now you understand how this is transmitted in this fashion. And this is a simplification of this, and this is a simplification of that. So that is the force part of it. What is the moment part of it? Moment resistance is that force be a times the distance from the neutral axis. So which is d minus a over 2. So the a value is beta 1c. You see that beta 1c? So what is beta 1c? This is American code, so I'm not familiar with your code, but they're all about same. Equilibrium cannot be different, right? So what is beta 1c? I'm teaching the American code. Up to 4,000 psi, beta 1 is 0.85. Up to 4,000. Above 8,000 psi, beta 1 is 0.65. So when you go to from 4,000 to 5,000 psi, beta 1 is 0.85 for F prime C of 4,000 psi concrete, right? That is approximately, what do you say? That's about 25, close to 25 MPa, in that range. Maybe a little bit more, 27 to be exact. So that beta 1 is 0.8 when F prime C is 5,000. That is the simplification made by the American code. And that number is 0.75 for F prime C of 6,000. That number is 0.7 for 7,000. That is 0.65 for 8,000. And it is still or greater. So that is the definition of this beta. Again, after testing literally hundreds of cylinders, we deal with a cylinder strength, not a cube strength. Okay? You all deal with cube strength. Right. So please note, I should have emphasized it up front. So now you know what beta is. It's extremely simple. So your moment resistance is B times A, that is the compression block area, corresponding strength, and D minus AO2. Oh, I goofed up, sorry. I should have added 0.85 here. Okay. So that is an approximation, but works wonderfully well.
In India, our IS code, it comes up 3.67 FCK.
Okay.
So nearly about 2.8.
Yeah, these are all calibrated. We calibrate it up front before we release them out. So that's what I mean. They're all highly calibrated stuff, you know. All right, now, I think some of you are not clear about what is a tension failure, what is a compression failure, what is a balanced failure. Unless you know what is a balanced failure, which is an idealistic failure mode, otherwise you will not appreciate what is a compression and tension failure. Okay. For a balanced failure, we say that, okay, here is the strain compatibility diagram. Okay, so for a balanced failure, we say 0, 0, 3. 0.01. I'm not saying that's right or wrong. I just don't want to get there. All I'm saying is that is what the code recommends. Okay. You know where they got that 0.01? That comes from 60 KSI business. You know, somebody thought, meaning 0.01 is the strain. E value of the composite is approximately 10 to the power 6. So 0.01 times 10 to the power 6 is 60,000 psi or 60 KSI. That's where there is no rhyme or rhythm for arriving at that. In my notes, you will see in the next slide or two, I certainly question this. But I'm not going to go there. My questioning doesn't make any difference. You have to follow the code. Why do I question that? Think about it. If you remember, I said typically I tested 500 to 1,000 bars in that range with your vinyl ester type thing. Typically, we are getting about 15,000 to 20,000 micro strains to failure. So, if I convert that to multiply this with 10 to the power minus 6, 1, 2, 3, 4, 5, that's what you get. Or it's more I was getting in this range. So they have reduced it by a factor of 2. Don't ask me why they reduced it. My feeling is, I was not there to understand it, but my feeling is they put it 0.1 because that corresponds to your 60 KSI steel. I think that's what they did. Somebody was asking me the question, where did you get 0.1? You know, that's what it is. Okay, now, if it is a balanced failure, some of you, most of you know that we are talking about concrete reaching 0.03 while at the same time FRP at 0.1. That's a imaginary idealistic framework, whereas it may not be true. Okay, if I want concrete to first reach 0.03 or 0.035, you people use, the Germans have 0.04. If you want concrete to reach that number before FRP reaches this number, that implies that is called a compression failure mode under bending loads. We have to be very clear. Because somebody asked me a question, I was a bit aghast that, oh, gee, I didn't explain it right. Okay. So in such an event, when will you get that? Only when the neutral axis is below the balanced value. And conversely, if I want a tension failure, it goes up and you know the rest of the story. Okay, now, why did we pick compression failure mode as a preferable failure mode? We never said you should not use a tension failure mode. Nobody said that. Between the two, we prefer a compression failure mode. Why? Because when we look at, I was looking for it, I didn't find it, but the energy that it is going to absorb under compression failure mode for FRP reinforcement is higher than the energy absorbed under tension failure mode. That is the crux of the issue. Okay. Then, like I said, in steel, we have a preferential failure mode as tension failure mode, not a compression failure mode. And there was, like I told you earlier in an offhanded manner, a tremendous resistance to accept compression failure mode with the GFRP because the mindset is that. Then we have to show here are the energy absorptions and then the deformability ratios are superior, blah, blah, compared to tension failure. It's all a relative statement. May not be as good as that of steel, but you still have a good bit amount of warning. Why are we using this? Because we need adequate warning to prevent catastrophic failure. That is the primary reason we are having it. So in that sense, the compression failure mode compared to tension failure mode with GFRP is superior. Only in that sense. Is it superior over steel? I didn't say that. Okay. Then we are trying to compare and make some kind of, how the human tendency, let's see if we can make it as close to steel as we can, right? I mean, that's natural anxiety, no doubt. Then we establish the curvature. You will see the curvature of these systems is around 0.016 to 18 divided by D. We'll see that also, which is also closer to that of steel. Not same, a little bit lower, but somewhat closer. Okay. So that was the argument why compression failure mode is a preferential failure mode with GFRP. So I think I gave you enough fundamentals here. I can hopefully move forward. If there are a couple of things I missed by some reason, I'll reiterate it. So,
it is the same. For example, if we will go for the doubly reinforced beam or something like that.
Again, if you go with the doubly reinforced beam in the compression side, what did I tell you? The code is saying the compression reinforcement is only as good as that of concrete. Therefore, doubly reinforced beam has no special advantage over the singly reinforced beam. I don't agree with that. Personally, I think they made a mistake in my opinion. I shouldn't say they made a mistake. They took that route because that is a conservative route. That's what they did. They're not wrong, okay? But they're not right either. They're not wrong because that is the lower bound. See what I mean?
We simply want the concrete to fail first.
That is the definition of a compression failure mode. Right. That's correct.
Because the GFRP failure first will be catastrophic.
Exactly right. There are other things associated with it, like what? We are going to have GFRP ties that would provide a confinement effect, and that would further increase the ductility plateau. But they are ignoring all those kinds of things, so let's keep all those aside. But with this argument, if you going to use as a tension failure mode, you are permitted. I told you that, right? Not the preferential, but it is permitted. If you go to that, it becomes uneconomical.
Yes, sir.
That's what it is. Okay, now I will go. Did I skip anything? Okay, no, I didn't skip anything there. So I already gave you. This is the compression failure mode. You look at that. What is that? Area times FFU. That's the lower bound. That is the balanced value. The balance is established based on your compatibility relationship. it doesn't show on that screen. Compatibility relationship. Where did you get this thing? That thing comes from here. So, with that, I talked about beta 1 issue already, and this is the complex curve that is idealized as this, and that is the balanced failure. What did I say? I said the balanced failure definition is 0.01. I wrote it there, right? Okay. Now, I further stated here, beta 1 is 0.85 up to 4,000 psi, decreases by 0.05. I wrote it down there too. All right. Now, I'm explaining it because our code is slightly different. Like he said, it all washes out to the same thing with a few percentage point this way or that way. That is tension failure. I already told you that the neutral axis is going to be shifting up smaller than the balanced value. That is the tension failure. What is a dowel action? What is a dowel action, do you know? It is a shear transfer by the composite. They neglect the dowel action, shear transfer, even by steel, forget about the composite. In other words, they do not account for the dowel action. It's a friction. Actually, it is the shear of double bar. Somebody was asking me about the double bars. So there's a shear force transfer. So that transfer, and we are not accounting for that kind of a thing when it comes to composites. Even in steel, we measured it. Some of the dowel actions are like about increase the strength of the material by about 15%, you know. But we are not accounting those kinds of things in real mass designs. We may do that for research purposes, but not for design purposes. So that's called, first of all, I want you to understand the dowel action, shear transfer. Ability for the FRP to resist shear by itself. Forget about the contributions coming from concrete, forget that. But by FRP only, that is neglected. As you know, the shear stress to failure in steel is about 40 KSI for a 60 KSI steel, roughly. Whereas in an FRP, it's only 5 KSI. So it's not really contributing a whole lot. You know, the shear modulus of steel, you know how much? 30 million PSI is in tension and bending. You know the shear modulus of steel? What is it? G is equal to E divided by 2 times 1 plus mu. That's about 40%. 1 over 2.5 or 2.6, you know. So that's why we neglect any kind of a shear transfer by the This is the reason why they, upfront I told you, you may have not registered it in your mind. What did I say? They do not want to have any kind of shear-based enhancements. Zero. Now you can find Mn as a nominal value. What is a nominal value? That is before you multiply with the reduction of the resistance factors. That's called a norm. If you multiply with a phi factor, that becomes your M sub u. Okay. axial and combined axial flex strength. Here, if the axial load that you are applying, what's P sub U? P sub U is from the induced loads, but most importantly, multiplied with appropriate load factors. So you need to understand and clearly differentiate this, or else you can be mixed up. That if P sub U, only if it is greater than 0.1 F prime CAG, then stresses in GFRP is limited to what? 0.01. In other words, then only that is the combined axial bending effects. If P sub U is less than that, for all purposes, you say it has no bending effect. That's again an approximation. Okay. Only after the axial load effects are higher than 10% of the ability of the concrete to take the full capacity load under compression, then only, okay. I don't know how you do, in US we assume axial loads or columns compression design are automatically multiplied with a factor of 0.85. The reason we multiply that is because there is no way in the world you are going to get 100% perfectly straight column. So we feel there is always certain degree of eccentricity. We cover that eccentricity with this fudge factor of 15%. So I don't know, I think you will do that. You do.
Size effect also.
So, that comes. These people, as you know, they are very silent on size effect. They don't want you to get in there because we don't have columns tested that are 6 by 6, 12 by 12, or 24 by. So we don't have that. Yeah, I understand in the steel they do. Yeah, I'm going to talk about size effect in only one scenario. In terms of, we have surface reinforcement. Steel guys say you can keep the surface reinforcement designs in an empirical sense up to 30 inches in depth, whereas we say only up to 18 inches in depth. And there is now as I said, this is all rule based other than this equilibrium equation I wrote there. Other than that, every bit I'm going to be talking about is pretty much rule based. Of course, we keep that in mind. We're not going to violate the equilibrium. But the rest is rule based, you know. Okay, yeah. So the first point is that one. If PU, which is inclusive of load factors only, exceeds 10% of that, then only we treat that as a column with potential bending, or else we say it's a pure compression, no bending. Okay. Bars, I told you 100 times. Bars in compression, please note how many times I said, treat GFRP as the same strength stiffness of surrounding concrete in compression. Okay. I need to, as a person standing up teaching, I need to at least say that is nothing wrong with it. It is on the conservative side, but they could have easily multiplied that with a factor of 3 or 4 for the load taken by the bars. But anyway, that's just a sidebar issue. Typical balance failure, I already told you and I wrote it there, 0.01, but I put some people can question that. GFRP in axial compression will not contribute much and neglected or equal to F prime C. And this is a standard compression formula. Maximum axial strength in ties is 0.8. Nominal axial strength is, again, this This kind of a concept is repeated over and over again. You know, there's nothing I'm saying new. Now we are in the design mode, so I have to repeat it to make the story complete. That's all. So C is the correction factor, this is the adjustment factor, that is the area of FRP. Okay, we neglected the double action, what have you. Now, again, these are all rule based, right? So what is that telling us? The closed loop ties have a clear spacing of 4/3 of the size of the aggregate. Typically, we use 3/4 inch aggregate. I'm not saying that's the only one. We use also 1 inch aggregate size, you know, maybe 1 1/4 inch, depending on the size of the concrete, a beam or a column. But typically, but the message is that that is one. The second thing is center to center spacing of the ties is 12 times the diameter of the longitudinal bar. This is called the longitudinal bar, or 24 times the diameter of the tie or the stirrup. We use smallest of the dimensions. Minimum bar diameter, there's no, I don't know what you are doing. In US, we don't have a number 2, meaning, what is the number 2? 1/8 inch size bar. We don't have it. I don't know, you have it anymore. So we use typically 3/8 inch bar. That is what? 3/8 inches is 9 millimeters, right? Yeah, you use 8 mm. We use 9 mm. And typically our stirrups are 9 and 12 mm. I'm not saying we don't use 15 mm, we do, we go up to 18 mm, but we don't use stirrups beyond 18, but by and large, our stirrup sizes are 9 and 12.
Here it is 8 and 10.
There we go. Yeah.
Rarely we go up to
12, yeah.
We use very here.
We, again, when I said we use an 18 mm, that's rare. I'm not saying we don't use it, we do use it, but not common. We try to restrict it to 9 and 12 or 8 and 10. That's our typical size. So the anchorage of ties shall be provided with standard hooks and engage the longitudinal bar. Like, what does that mean? Like the one we are showing there. That is an issue. You're absolutely right. But I'm only speaking what code is saying. Now, if you allow me to speak, I have a lot of questions about it.
Even when we talk to manufacturers,
It's
they
not
give
po-
only the 90-degree bend, not the 135.
Therefore, they use that U-shape.
U-shape.
That's right.
Even if it is closed also,
Then you overlap it. Yeah, I know. But this is a code language, not my language. So I understand the practical difficulties. Yeah, I know. They asked me to, they didn't like me because they asked me to chair that committee. I said, I'm not going, I don't want to waste my time. So they didn't like that. Anchorage of ties shall be, okay, we said that. Minimum overlap of bar ends. This is very important, meaning from, when the bar is ending, you need a certain overlap type thing for the force transfer. Again, where did you get that? I mean, these are mostly empirical. And they're also mostly taken from the steel code. What their argument is, oh, it is working for steel, we're going to make it, it'll work for, till it fails, don't fix it till it, that's what that is. So you need to keep these in mind when you are concluding a design. Remember, I always tell my students, the devil is in detailing. If you don't detail properly, finding the bending moment and the shear cap has no meaning if you don't look at all these kinds of little things that do not have an equation to follow. So, for some who may not know, the left figure is the tie, this is the spiral. And the spiral configuration gives you a better confinement of concrete. Therefore, we have a more favorable equations for spirally reinforced beams and columns compared to tied columns. Not much, but it is. The factors are 0.8 versus 0.85. So tied is 0.8, 0.85 for
Spine.
another limitation we need to make sure is, now the shear. I told you we really truly dumbed down the shear part of it. It cannot be dumber than that, you know. It has two parts to it. One is the concrete part, the other is the reinforcement part contribution. And again, this is the resistance part, and this is the area times 0.2 F prime. This is very, very standard. But keep in mind, BW is the web width for rectangle and diameter of solid circle. D is 0.8 BW for circular sections. Okay. So these are coming again from the code. All right. So this is an interesting thing. So if you go back and look at it, we have two components, right? One is concrete, the other is GFRP. Now let's look at the concrete. I don't even know, honestly, me talking, not the code. They have two equations there. They're saying greater than 5 times lambda S KCR square root of F prime C BWD. So BWD is the area, right? Yes. We know that. So 2 times, typically 2.5 times square root of F prime C is what the concrete shear contribution. But what I didn't quite understand is, we can talk about the lambda S. For a minute, let's assume lambda S is equal to 1 for discussion purpose. So what is the first equation versus second equation? That is 5 times KCR times the rest versus 0.8. That's essentially the difference between the two. Am I right?
Yes.
Okay, good. KCR, I don't know how many of you, do you remember how to get that KCR at all? You don't remember. What is KCR? KCR is what is the depth of the compression block at failure. You know, that is the key. That's what we are talking. And like I told you many times, it is hovering around 0.1, 0.12 in that general range. So if I really multiply 5 times 0.12, I get 0.6, right? And with all the approximations, why they wanted to sound like a super sophistication with that equation, I have no idea. Number one. I can derive that equation in no time. But number two, this value is so small compared to that value. I don't even know why they have included this term under the square root. I have no idea, but that contribution of this second term is totally negligible. shear strength modification size factor. You know what a size factor is? You don't. Okay. Timoshenko shear, if you look at it, size factor is a ratio, is a value based on the ratio B over D. If B over D is nearly square, it is about 1/3, nearly square, plus or minus. But if that increases, 1/2, 1/4, it may come down to 0.25, 0.2. That's the kind of a size factor. But typically, in any design, maybe I should have started with that. When you design or want to design a beam based on steel under bending, where do you start? L over D ratio, L is the span length, D is the depth. Where do you start? The number is around 17, 18, 19. L over D should be 17, 18, in that range, right? In FRP, that number is 12, 13. Okay? In that range. Somebody say 11, somebody say 13, but give or take, that's what that is. So my message is, you don't have to be overly concerned about lambda S. You put 1 or 1.2, that'll take care of it. If you don't know it, go to your good old Timoshenko strength of material book. Maybe you use some other book, then go to that book. It'll tell you what is the shear coefficient for different aspect ratios of width over depth. Okay? So you can do that. But if you don't know it, in that absence of it, take it as 1. I'm not suggesting it is 1, remember. All right. Then, that is, if you are going to, I said it as 1, if the reinforcement, you have certain minimum reinforcements you have to satisfy for the stirrups. And the factor is essentially given here. If my D is 10 inches, that factor is 1. If my D is, let's say for discussion purpose, say 20 inches, for example, that factor is 0.8. 0.81 or something. See, so there's not a whole lot of difference. That's why I said use, in the absence of it, start out with 1. In the absence of any great revelation, start out as 1. So these are rules. That's why I said rule-based design. So finally, neglect axial compression in KCR computation. So what is KCR? KCR is the depth of the neutral axis under a compression failure mode. We are going to be assuming that the stress-strain response is linear. That is the catch. And you know what? In this is the stress, right? Of concrete cylinder or block. This is strain, right? This number is 0.003. We said that, right? This number, strain is 0.02. This number, 0.001. You know what 0.001 is? Up to that point, which is approximately 45% of F prime C, up to that number, we are saying that the stress versus strain in concrete is linear. That's what that number, that magic number 0.001, this is That's what we are talking about. Okay, anyway. All right. So, if I use the strain compatibility, if I use the equilibrium equation, if I use the force deformation relation, which is the Hooke's law, if I use all three and make it into one equation, that's what you're going to get. I'll be happy to derive it. Let's not waste time on that. Any rudimentary sophomoric textbook has it. That's what you're going to get. Okay. One-way shear reinforcement for, what is a one-way slab and a two-way slab? Do you know?
Yes, sir.
The aspect ratio is less than 2 to higher than 0.5 between. It's a plate action, the del 4 equations and what have you. It comes from the, some people use 2.2, 2.4 for the one-way slab. Above that is a one-way slab, below 2.2, 2.5 is a two-way slab. So what's the difference between the one-way slab? The two-way slab is stiffer than the one-way slab. That's essentially what it is. The two-way slab has a two-way bending. The one-way slab is like a cylindrical bending, and which only we call it a one-way bending. We only put the reinforcement in the other direction, again as a rule base with some kind of AS minimum type thing, the temperature and the shrinkage and what have you. All right, now that's the difference. Okay, so we are talking here one-way slab, not a two-way slab. The next slide maybe, I don't know that, but huh? Yeah, shear, yeah. Here, if you look at it, talking about slabs, my following statement is valid whether it's a one-way or two-way slab, but in a slab when there is a load, the corners are going to lift up. Means even though it is downward loading, at the corners you have a tension. So you need to make sure, and that tension zone is so small, you need to make sure that there is adequate tensile reinforcement at the top as well as the shear reinforcement at the, so you need to be careful. Now we are talking about design, we're not talking about some esoteric stuff. This is a hardcore engineering. So that's where you need to be careful when you design a slab. Okay, here, one way, again, the equation is same, isn't it? This is my resistance factor. That is my ultimate load. And this plus this is what I want it to resist. See what I mean?
Yes, sir.
That's what it is. So I'm now trying to find what is the magnitude of shear that the FRP need to resist over and above the concrete, And shear strength, transverse reinforcement, resist shear after diagonal cracking. Shear tension is more brittle than the shear compression. So we are more worried about the brittle failures than the ductile failures. Modes of failure depend on the reinforcement. And nominal shear strength, what that is? Of a stirrup? What's that? That is the area of the stirrup, that is the strength of the stirrup, that is essentially gives you how many stirrups you have in a given depth, because the shear crack is assumed to be 45 degrees. That's how you get that. That the number of stirrups, B over S prime is what? Number of stirrups that are cut by a 45-degree angle of the shear crack. Okay. So from all that, you are going to get by substituting all this here, that is the equation you're going to get, and I can define all this. So what am I doing here? What is my spacing, right?
Yes.
So I'm going to pick a number 3 diameter bar or a 4 diameter bar, therefore I know the value of the area of that bar, right? So here is the shear force including the load factors. Here is shear resisted by concrete including the resistance reduction factor, and this is what that amounts to. So that will give you the spacing of the stirrups. So from this equation, I know everything except this. So I find the spacing. Okay. Now, that's so far so good. So if you look at it, two-way shear strength with factored slab moments resisted by column. If you don't know what that is, I'll explain that later when I'm going to design a detailed, very detailed 14-page design example, or 14 slide I should say, design example for a two-way slab. I'll explain all that at that point. I'm only introducing the code right now. All this will be repeated when I deal with beam bending, shear values, one-way slab, column, the interaction curve, and finally the two-way shear. So I'll repeat all, but this is the code talking, not me. So the factored shear stress, okay, along those lines, I even told you where you can find these statements from the code. So what is a critical section?
It is the section in which the column is trying to punch
through, and a distance d from d by 2 or d from the face of the column all around. That is called a critical section. So that is where they have defined some of these things. Okay, now, so again, most of these are empirical in nature. The factored shear is factored shear stress on a slab at critical section due to gravity load and no moment. Shear stress from that factor gamma, MSC, applied at the center of gravity of the critical section. So what is gamma F? Now, this is an empirical equation, right? So I have to define from here what gamma F is. It's a factor to find the fraction of the moment transferred by slab flexure or shear eccentricity at the slab column junction. So again, they gave you a guide. That is, 60% of the moment is transferred by flexure across the perimeter of the critical section, 40% by the CG of the cross section. So these are some of the rules given by the ACI code, and the sections have been defined. The higher number, like chapter 22 or whatever, gives you all the detail, whereas chapter number 8, that is chapter number 8, and this is chapter number 22. 22 gives all the nitty-gritty detail. Chapter number 8 gives you general guidance for the design. It doesn't give you, it'll say gamma. It doesn't tell you what that gamma is. So you have to go to chapter 22, section number 6, you'll find that gamma. So we define that, we'll come back and look at it in a greater depth. So you can see that D value, see the D value, so that is the critical section. So it is C plus D. So D by 2 to the left, D by 2 to the right. I'll give you the critical section. And there is a procedure there. We will talk about that later. So the factored shear and the factored slab moment resisted by the column are given to you. Again, these are all rule based, right? So now we can modify the JC, that is essentially like a polar moment of inertia. It is analogous to that, you know. So this is the equation. Maybe I should have put the equation number. I did not put it, but I did provide the section numbers there, but I did not, I mean in the previous one, but I did not provide the equation numbers from the code. And if you open the code, you will find the equation numbers. And these equations are essentially same as those in the ACI 318 code. And please don't forget, the mechanics part didn't change, the materials part changed. So that is one thing you need to keep track of it all. So we're back to our same philosophy. Phi is the reduction factor for the material, and S is the strength. We in the US call stress as strength. Don't ask me why. They call it strength, you know. I don't know where that word came from. What that means is essentially the stress, but that's what they mean, really. Okay, U is coming from the factored load combinations. So phi times Mn, which is Mu type thing, whereas Mu is a combination, load combination based moment capacity. You will understand all this when I run an example very, very quickly. Okay? So again, the approach is same, whether it is a beam or it is a slab. For the slab, it is modified by gamma factor. Why gamma factor? Because we have a sharing effect of the slab, beam, and the column. That's why that factor, they're not going to let you compute it by yourself. They gave you an actual number. And the same approach for shear. Slab design shear near columns, concentrated loads, and you remember I told you that the plane sections do not remain plane, you remember? And I said they gave you a guidance, you remember? Where you have an opening, where you have a, what do you call it? A drop panel? What do you call it?
Discontinuous.
Yeah, discontinuous function. But a drop panel is a, yeah. That is where all these, here I gave you the section numbers. As I said, this talks in generalities. In chapter 8, the specifics are in these chapters. Please look. Permitted if the analysis shows strength and service limit states are satisfied. So this is quite a task. You have to have a lot of patience to crank through these numbers, you know. So the reinforcement limits, you need a minimum amount of reinforcement. Why? Not only from the standpoint of temperature and shrinkage, but also you need a minimum reinforcement due to what? You do not want to have a reinforcement that is less than the needed amount when there is a first crack. So minimum reinforcement is always tied to the M cracking, or else what happens? You have a catastrophic failure. When the crack happened, if there is less than the minimum required, then it's going to collapse. So that is why you need a minimum. That minimum, they are defining it there, 300 AG divided by FFU. Again, there is some physics behind it, but primarily an empirical value. Of course, there is a physics, no doubt, but mostly empirical value. So the reinforcement is 3 inches of cover. There is a difference between a clear cover and cover. I suppose you all know that, right? Clear cover is, let's talk about cover is from the extreme fiber to the center of the reinforcement. Clear cover is minus that. Correct. So please keep that in mind. So 3 inches for cases with having permanent contact like foundation, 2 inches for number 6 to number 10, and 1.5 inch for number 5 and smaller thicknesses, 3/4 inch for slabs and joists. These are minimum values. 1.5 inch for beams, columns. Again, they call, I may have it here, they call for a 2-inch clear cover for fire, under fire. So keep that in mind. Development length. This is very similar to steel. Slightly modified, but very, very. Reinforcement location factor is 1.5. That is psi, that's a Greek letter psi, T for 12-inch fresh concrete, or 1 for other concretes. CB over DB, whereas CB is the center of the bar to the nearest concrete surface, or center to center bar spacing, that is 3.5 to avoid splitting, or else you are going to get into cracking of the cover, concrete cover. So these are development length, for tension terminating in standard hooks, another rule-based equation. We talked about strength reduction factors, bending moment, axial force, or a combination of axial and bending. So you can see the phi factor is 0.55 to 0.65. 0.65 for compression failure, 0.55 for tension failure, and here when you have in a column between the two, including the bending, EFT, that is the strain in the tension side, 0.8, and that is epsilon T. So you have to determine what the strain values are and then establish whether it is in tension or compression. As I said, the phi factor is tension control and having a minimum reliability of this. If you remember, I told you the curvature of FRP, glass FRP based failure, we have found after 2030's test, 0.016, I already told you, in this range. For tension, 0.11 to 2 divided by D. For compression control, you can see what it is for steel. So we want, again, remember, we want the curvature to be closer to as much close as possible to steel, but that's not coming out. And this helped in terms of energy absorption type thing. That is where our compression control design is coming into play. You know what a curvature is? Curvature is, you know what it is? How do you define a curvature? It is the slope divided by d. Here. This one. Divided by d. That's called curvature. Slope has no units, right? Curvature has 1 over length units. So dy dx is non-dimensional, right? Comes from there. So, another approach you might want to consider if you want to design these beams is think about equating, somehow getting the curvature. You can, once you know what that slope is, right? Once we are telling you, if you want a compression failure mode, you need to maintain this. Now you back calculate. What is the AS value or a GFRP value, not steel, you want to have. You understand what I'm saying? From a designer's point of view, that's another, as opposed to, I told you, where do you start a design? L over D of 12, right? Something like 11 or 12. For GFRP, about 17 or so. For steel, that's one way. The another way is you are guaranteed pretty much to have a compression failure with this kind of a curvature. You put it in there and back compute all the equations and the numbers. If you don't know how to find those K, CR factor and what have you, you can refer to my book I wrote in 2007 on concrete alone.
Sir, another parameter to know whether the failure is tension controlled or compression controlled? Any other parameter?
Well, only, there may be others, I don't know, but we found two that work very well. One is you start with L over D of 12. The other is this one. So that's a starting point. I'm not saying that it will be foolproof. I'm not saying. Then you have to make a check and balance. You have a question, sir?
Sir, I wanted to ask you, sir, like what is the reduction factor for compression failure?
What is what?
For compression failure, what is the reduction factor?
0.65. Yeah, it's written right there. Oh, I thought I did somewhere. Somewhere it is there. 0.65. Huh?
That's slide only therefore.
Oh yeah, there. Please look. Yeah, anything dealing with compression type failure is 0.65. Anything dealing with tension type failure is 0.55.
But in the axial force calculation, you have shown 0.85 into FC prime.
That is pure axial.
That is pure axial.
That is pure.
That's pure axial. Wait, that's one aspect. The other aspect is, I did show, I can get a bending moment from this equilibrium diagram. And if I, based on this approach, if I from here I know the balanced value, right? So if I'm going to have my depth of the compression block below the balanced value, then I have to multiply all this with the phi factor. First I have to establish, is it a tension failure or compression? If it is a compression failure, I'll find the bending moment M sub n. Okay, I better make this very, very clear. Okay. So from here, I'm going to get, where is this? I thought here. This is what we call Mn. That's what we call.
That should be multiplied with phi.
Exactly. This should be multiplied with phi, and this should be higher than Mu, where Mu is the one with the load factors included. I'll repeat all this in a design example. I'm just doing this like the code did. First, so many chapters are theory, or whatever you call it. Then the other chapters are the nitty-gritty. So this is very, very critical. This approach is going to be...
Actually, sir, in our IS code, we do take the factor of safety in material and load, but whatever moment we calculate, we take it back as a strength. So here in ACI code, we put the factor of safety in the nominal moment capacity. That's the difference. I think that's why.
Before calculations, we multiply with the partial safety.
Partial safety factor in material level.
Okay.
And we calculate moment and we use that. But in ACI and all, we use that factor of safety after calculating the moment.
Correct. So I hope I'm not confusing you. No, I mean, yeah, I know. But it amounts to the same thing. That's the point.
So like when you do calculation of development length, we need the diameter of the bar. So that diameter of bar, there are two diameters. One is provided by the manufacturer and one is the actual one, which is calculated by the test.
Consider the actual diameter.
Please use whatever the manufacturer is suggesting as the area for his. They are supposed to give you the actual area as well as your FFU type thing. You see, you are not, as a designer, you are not responsible for it. But if something goes wrong, the manufacturer is going to be sued. Because you are, as long as you are using what he is giving you, you're okay. I mean, we don't want anybody to have a problem, anybody to have a failed structure. That's not the point. The point is, make sure that they have responsibility to provide you with accurate stress values, design stress values, not the average values. Remember, the three different values we are talking about, right? Okay. So, and also corresponding area values. So in ACI code, if I remember right, we are asking the manufacturer to tell the load that a number 3 bar carries, number 5 bar carries, number 8 bar. We're asking them to tell so that people don't get confused in terms of this so-called size effect. You see what I mean? Because of this shear lag effect. People think like in steel everything is same. By the way, I suppose you all know even steel has a shear lag problem, except that shear lag is maybe 1 or 2 or 3%, not like 30 or 40 or 100% in FRP.
But that is a higher diameter.
Right. You see, in a microscopic sense, even at a lower diameter you have, but you don't find it, as important. You don't find the variation to be very high. That is why when you test the higher diameter, you find that cup and a cone type of separation failure. You see what I mean? That's more pronounced at the higher diameters, right? Not so much at the lower. Okay. So So the phi factor is 0.65, and the curvature is for compression failure is 0.01102. 0.011, I don't know where we got that 0.02, I'm not sure, but anyway, keep that in mind for compression, and that is very similar to that of steel. Very close, very close. I don't know where that, I need to go back, check 02. All right. So, we discussed the issue about beta 1 factor. I already told you how it varies in our. Do you have a rectangular stress block concept here too, or you don't?
We have a rectangular with a parabola.
Rectangular
Combination.
So you have to have a much more complicated mathematics, I see. Okay.
After the
also-
straight portion, we have the rectangle. After that, the
Yeah, that is originally that's what Jensen created. Essentially, you are telling me it is something close to this. So you have a parabola of some
that
kind.
we have a parabola.
Right, right.
The code is suggesting the depth and the neutral axis.
Right, just like we suggest. Okay. Yeah, yeah. Yeah. Yeah, that was one done by Jensen, 1951. Okay. So, that is that beta factor, you know. That is that beta factor is what we talked about. So again and again, this is the third time I'm writing here. It is saying in compression, GFRP is okay when it is treated as the same as the strength and the stiffness of the concrete. This is the third time I wrote. Tensile strength in concrete is neglected. This is same, somehow I had a duplication of that as this one. All we are discussing is summarized here. Okay? So, any questions? Maybe we should stop for a few minutes and see any questions from your side. Then we will move on. Maybe from online people.
So there is one question that
Sure.
I would like to ask you, sir. So in the steel, for overlapping, so there is a overlapping length is there. That overlapping length is different from the compression steel and also the tension steel. Similar to that, even in FRP, the overlapping is allowed, or maybe.
Overlapping is absolutely allowed.
But how do we do the process?
Okay, now, if you saw here, I gave you an equation for overlap in the tension side. You know, what they are saying is you don't have many issues, so we can follow the overlapping, that L factor I talked about, as in steel. For compression side. For the tension side, they gave a different, yeah. So, again, we always like to calibrate against steel-based systems, and that's what we did. And any code, we calibrate it against existing materials, such as our bridge code is done that way too, but it took us about 20 years to really refine it to the point all the systems are debugged, you know. So any questions up to this point? So I concluded the flexural strength equation here, and one thing I mentioned, shear between the topping and the precast concrete with GFRP across the interface is not covered, and no distribution, no distinction between the shored, unshored member design is, you know, they're treating it as same, both shored and unshored, but the shear between the topping and the precast concrete with the GFRP is not covered. You know what that means? You remember I did the bridges Some bridges I did put the FRP, GFRP based concrete on top of pre-stressed beam. That is not covered because we're not sure whether any of the protrusions are going to adequately carry or shear transfer type thing. Okay?
Yes, sir.
That's not covered. Again, we don't have enough data to say it's good or bad. So here I've shown all three: compression control, balance, and tension control. So here, as I told you earlier, for a spiral-based columns, we have a slightly higher advantage compared to the tied columns. 0.85 to 0.8 times P sub 0. Again, I said the balance condition is 0.01. And the ties and spirals for lateral support of longitudinal bars in compression, please follow table number whatever as spiral requirement at column top. So this is coming straight out of the code. Max axial tensile strength is a nominal axial, we call it nominal, should be greater than or equal to PNT max. That PNT max equation is given there. And for the bent bars, it is a similar kind of a scenario as we discussed. These are, so here, one-way shear, I have explained that already to you. Again, this is a repetition. Maybe I did not explain one important thing, that we do not want to take f prime c greater than 100, square root of f prime. In other words, f prime c is 10,000. That is the 10,000. Therefore, this code is restricted up to, you say 10,000, but we say 8,000. That's what, in other words, we are not sure what happened for a high strength concrete. That's the message.
So in the formula case here, there is a rho f and is it the percentage of?
Yes, rho sub f is equal to the area of GFRP divided by BD, where D is the effective length, not the, effective depth, not the full depth.
So here, that means indirectly we are trying to see the contribution of the fiber bar in calculation of the VC. Mm-hmm. That is nothing but a kind of double action.
Okay, okay.
Generally, when we are calculating the shear strength of the concrete section, so there is uncracked portion will be there, and interlocking of aggregate will be there, and also the contribution of the shear resistance from the rebar also will consider in the calculation of tau c, that is permissible shear strength.
Let me say this. We do not consider any interlocking advantage you have after the concrete crack in GFRP, like you do consider that in steel-based one. Let me make that crystal clear. The reason is the crack widths are much higher than those in steel-based, and by the time, you have to have certain lower ranges of crack width for interlocking effects to take place. But if on the other hand you mean when I am doing this, I'm balancing the forces resisted by rebar, that's correct. Yeah. So I want to be carefully differentiating between what you all call dowel forces vis-a-vis what we call. For us, a dowel force is strictly force taken, shear force taken by the longitudinal bar.
But even in our code also we call the same thing.
Okay.
The shear resistance offered from the rebar.
Bar.
is the dowel.
Right. But you folks, it seems to be interpreting the shear resistance as a dowel force based shear resistance. That's what.
That is included in the calculation of the concrete strength itself.
Okay.
So in our code there is a concrete strength,
Right.
which takes the combination of dowel and interlocking and some other
The percentage of reinforcement and also the concrete strength. It's
Yeah. But we don't consider any dowel force.
Yeah, actually, bond is less for GFRP with concrete. That's I think
Sure.
bond between GFRP and concrete is lesser than that of steel and concrete. That's why the dielectric will
No. Bond of GFRP and concrete is slightly higher than that of steel and concrete. For design purposes, we don't differentiate any major difference in the bond strength. In other words, we assume bond strength is same, even though bond is slightly higher in GFRP than in steel. For design purpose, we assume the same. But of course, that equation, that KCR type equation we are talking about here, that is where the concrete is resisting the shear effect, and that KCR is the one that what we call the depth of the neutral axis.
the depth of the uncracked.
Uncracked, yeah, that's the right word. Uncracked concrete. So there is a slight difference the way you keep using. I'm not saying you're wrong or anything. I'm saying we don't use. Yeah. But that's what we do. You get it? Yes, that's the right word. KCR is the depth of the concrete that is uncracked. And that comes from essentially your strain compatibility equation. Yeah. So you see what they're saying is in that, as I told you earlier, 12-15%, typically that is in that range. I think really I picked that number from the code, but I can challenge you that's on the higher side.
So one question has come, but you have described that from where that 0.01 strain is coming.
I gave you the reason where it is coming, right? I'll repeat the reason. Is he listening to it? Okay. Typically today, the average modulus of GFRP is in the range of 6 million. Average. Somebody may say 5.5, somebody may say 6.5 million. On an average, it is 6 million. If you are trying to tell me that the balanced ratio of a steel reinforced system is such that I have 0.003 for concrete strain to be balanced with 60 KSI divided by EY, which is 0.02. If that is the premise, I'm using that 60 KSI and I have arrived at 60 KSI divided by E of FRP, which is 6 million, that gives you 0.01. That is where it came from. I'm not saying I necessarily agree with that, but that's where it came from. I would have, if given a choice, I would have used a slightly higher value than that. Because consistently we have seen for a 60% fiber volume fraction, we normally get 20,000 microstrains to failure, not 10,000. That translates to 10,000 microstrains. So we'd have given a slightly better, but they don't want to. I know where they. Let's consider this as a lower bound. The reason is Even though I'm getting 120, 140 KSI to failure for lower diameter bars, for higher diameter bars like a 1 inch, I'm not getting more than 70 KSI. So they took it 60 KSI as a lower bound. So they have a reason for it, I don't deny that, but that's the reason. Let me not go any further.
Sir, if we are testing a concrete beam under 2-point load, and if it is in compression failure, whether it is a crushing of concrete at the compression side or we are getting some flexural crack at the bottom.
Definitely you get flexural crack at the bottom, but definitely there is a compression crushing failure at the top in compression zone, but the GFRP does not exceed a strain of 10,000 microstrain. That is the point. If GFRP exceeds 10,000, then I defeated the purpose of my computation here. See what I mean? So it cracks. Crack grows, there's no doubt. But the strain in the GFRP does not exceed 10,000. So KCR, like he correctly said, uncracked zone. And that zone, again, for all purposes, you can take it as 0.16 as per the code. I would take it more like 0.12. The reason why they take it as 0.16, let me say this, they are correct, maybe I'm wrong. The reason they take it slightly higher, they are not looking at KCR at crushing. They are looking at KCR at a workable level. You see what I mean? They are not looking at failure. In other words, it is something similar to I cracking versus I effective. That is, at the service load levels is what, then they're absolutely right, that 0.16. Yeah, somebody has a question? Okay.
Not until the numericals and calculations.
Okay. Size effect, we talked about it. Again, it's a D over 10 type thing. Typically, we don't want to go more than 20, 24 inches in total depth, you know, which means the effective depth is about 22 inches for a 24-inch type thing. So you're talking about a factor of 0.82 due to the size effect, okay? Same equation, but I gave you the equation number now. Now we can go to the shear, two-way shear. It's 3:30 already. They want me to stop.
Signal time is 4.
Huh? Yeah, I know. No. What I meant is Q&A session. Now it is 3:38 in my phone. Any questions from outside, inside?
You were saying that at this 0.01 ultimate strain for the GFRP bar is on the lower bound or higher bound?
The strain value is on the definitely lower bound. But when I said a minute ago or several times, we are finding it is about 0.015 to 0.02, that's what I said, right? But that is a valid statement without question for bars up to 3/4 inch and 7-inch diameter, but not necessarily, it is more like 0.1413 for a 1-inch diameter bars. That is where I need to be careful of what I said.
According to the code, 0.01 microstrain, 0.01.
0.01 strain, that is 10,000 microstrain.
That is given by the code.
That's right.
But they have not considered the variation in different bar diameters and different bars.
They did not. That is the problem. You see, If I remember right, the code did mention the minimum values of forces for different bar diameters. I think they did, if I recall.
Forces they have done, but not the strains.
Right, they did not do the strains. Yes, yes. I think if I remember right, they did mention the, unlike steel, there's only one value. Here we have different value. Therefore, they didn't want to mention in terms of strain, but they mentioned it in terms of force, not stress. Normally when we speak in terms of stress. But they did not mention that. I don't know why. Maybe because of the shear lag issue. Maybe they're worried people get confused with all this and use a wrong number. That's why they're giving you. That number, the 4 they're giving is up to the manufacturer to guarantee it. You have nothing to do with it.
Even in India, manufacturers, they will supply the specifications of the product what they are making. Especially the GFRP parts, they will quote what is the guarantee strength.
But really, they should also guarantee what is its strength or stiffness 50 years from now. That is the key aspect. That way, you are guaranteed of what happens to the structure 50 or 100 years from now. To do that, they need to at least adopt the Arrhenius equation that I talked about this morning. That procedure, I mean.
So what same, the steel binding wires are used to connect the mass.
Overlap.
Yeah, overlap.
I didn't catch.
In overlapping, the reinforcement, generally we tie with the spiral
We do
wires.
too. Yeah, we do too. We have a plastic ties. I don't know, zip ties we call it? Okay, okay, zip ties, that's what we call it. Yes. Yeah, you good to tie it, even though you may not need it once the concrete is settled, but before it settles, there may be certain movements in it. Good to tie.
Even after settling under the loads, when the member is bending, so that is the weaker portion.
No, it is weaker, but once concrete is cured, it's not supposed to bend or anything. The tie is not going to do any good, but it should, yeah. We use a zip tie. It's very efficient how they do it. I've seen workers doing in the field. Amazing how they do it. Yeah.
So generally in the bent elements, the radius at the bend angles, that gets distorted.
Mm-hmm. Sure.
And the other bent elements too.
Okay. Sure, we know that. I mean, typically that's about 2-inch radius, typically in that range, maybe 2.5-inch radius. That radius of curvature is.
No, not the radius of curvature, the nominal radius.
Oh.
I
Yeah.
am bending it before curing it. The only way that it will stay intact is from the partial curing method. If I will initially bend it and then I am preparing it for the oven, then the radius gets distorted, like it gets flattened at the bend.
Mm-hmm.
This will be get reduced.
The thickness gets reduced.
Right. Yes.
Apart from that partial curing method, what are the other methods that can be followed to keep that intact?
We don't have any method as far as I know. That is why what they're doing is they gave you that's a Japanese equation I gave you, works very nicely. When you test it, once again, that gives you a lower bound value. Typically, we are getting about 20% higher than what you get from the equation. Yeah. Look at my equation. That equation, no. There is an equation for, 0.3 for a tie, for the bend.
That exponential equation.
No.
0.05 into RB divided by KP plus 0.3.
That is the equation. That accounts for your bend. In other words, if you have a steep bend, like a V bend, you get a horrible value. in other words, it gets done. But on the other hand, if you have a 90-degree bend, you get a better value.
Yes.
And now the question is, how much is the radius of that bend, which is different from the radius of the bar.
Yes.
So there is a ratio between the radius of the bend divided by the radius of the bar. And then you multiply that with 0.05, and then you lump all that, subtract it from 1 minus that. So that is your stress concentration. You are reducing, that's essentially your stress concentration.
The same question I asked yesterday too, sir. The significance of the bend radius.
Right. Yeah, you may have missed it while we were talking today. I don't know what slide number it is. It is there. So you have the handout, right?
Yes.
Yeah. In the handout, we gave you that that equation.
Yeah, this is.
Oh, there we go. Yeah, that is 94. Okay? So, this portion, this part, is always less than 1. You see there? We are saying it cannot be higher than 1. And that part, for example, if this is RB is 2 inches, DB is a ½ inch type thing, that is 0.5. You see what I mean? So that accounts for the stress reduction due to bend. Well thought out, really, well thought out. But I'm a little aggressive designer. I feel these are a little bit on more conservative side. But that's again a philosophy issue, you know. I may know a little bit more about mechanics aspect of it. I can take advantage of mechanics, you know. But if you don't care, live with it. Okay. So we will, so we will look at the two-way shear tomorrow. And then we will run the examples, design examples.
So almost all the participants are, for first time we are exposing to the ACI methods.
Yeah.
So you have a little bit confusion with this.
Yeah, there is a minor confusion, I understand. That's why I'm also going a little bit slow about it. Again, the terminologies are a little different, you know.
I'm just waiting for the calculation.
Oh,
Trying to compare.
maybe what I might do, I will run a few examples tomorrow, then we go back to the theory part.
Yes.
Maybe that way you can relate it better. Otherwise, it's boring for you. Yeah, let me do that. Tomorrow, I'll start out with slide number, I think it's about 200, slide 200. We won't do all of them. You remember the slide number? 145.
This one.
No, not that one. They're asking, tomorrow they want me to start with the design examples. It's about 200, somewhere around 200. Okay, there. There we go, go back. There we go, 198. So we will run at least, I have 14 or 15 design examples, we'll run at least 3 or 4 or 5. Therefore, you understand the terminology, keep that in mind, keep track of what is MN, what is MU, what is phi, what is the load combination, all that, it's all written there. So yeah, we'll run about 4 or 5 examples tomorrow, then we can go back if, you know.
If you please go to ASA 440 once before you
Anything else? Otherwise, I understand the frustration. Yeah.